Hello, this is Dr. Han. I'll be lecturing you about Lab 8 titled Open Loop, Closed Loop, and PID Control. And this is prepared for ME 4234, Control of Dynamic Systems Lab. So, the servo arm. We have a servo arm in the lab, and then what's a servo arm? A servo motor is a rotary actuator that allows for precise control of angular position, velocity, and acceleration. And for this lab, we'll be controlling the angular position of the arm. So from ME3333, you may recall a DC motor equation, and then this is a specific type armature controlled DC motor equations, where the torque applied to the motor is proportional to the current instead of the field strength. So we have two equations where you're looking for what's omega, and the current. Okay, and the first equation is it just says sum of the torque, sum of the moment is equal to I alpha, where we're gonna use a J instead of I. Not so that we don't get confused between the I, the mass moment, and the I, the current. So you have J, mass moment of inertia, times alpha, which is the angular acceleration, which can be written as the derivative of the angular velocity. The moment comes from three sources. One of them is small damping, some kind of dissipative force, and you have a load torque. There's a little typo, by the way. Okay. So this one should have a load torque with a minus. Okay, negative sign is missing. And the third source is the torque provided to the motor by the armature circuit, which is proportional to the current in the circuit. Okay, so this KT is a motor's torque constant, and then this is a number that can be found in the data sheets of the motor that you purchased. So this will be the unit of the motor's torque constant will be Newton meter, which is the unit of the torque, and divided by amp. Okay. The second equation, it just says that input voltage equals the drop, equals the drop across the inductor, across the resistor, and minus, what's called the back EMF. Okay, so this is called the back EMF, and the constant, which is proportional to the motor speed omega, and the constant KB is called the motor's back EMF constant. Okay, what's the unit? The unit will be volt divided by radians per second. Okay, and believe it or not, those two, KT and KB, they have the same unit. If you do some conversion, you can find that the volt per radians per second be converted into Newton meter divided by amp. So we're gonna make, so this is a second order system. This is a second order system, and what do you know about a second order system? You have two characteristic roots. You can have up to two roots. They can be real, both complex, or both could be real and the same. Okay, so anyway, we're actually not going to use this equation. So what we're going to assume is L is small. Okay, and if you do that, this term will drop out. We can solve for the I and can plug it into the first equation. Okay, so we have a much simpler equation where it becomes a first order system. Okay, becomes a first order system. Okay, so this K, I really should write down C prime. Okay, C prime. Okay, so in this equation, this K, it's going to be a combination of some other constants. But the important thing is your input on the right hand side, is proportional to the voltage in. Okay, so what we did was we assumed, we also assumed the load torque, that was the other input, is also 0. So we divide both sides by J, and we obtain the following equation. And then we only do this to reduce the number of parameters to consider. So now we have c over j is a one parameter. We're going to call that beta. Beta is equal to some c divided by j. Okay. The reason why I'm putting prime is because when you go back to the previous slides, okay, what did I say? Solve for I, okay, and plug into this equation, okay, and you'll see that there's another term with a kb divided by r that gets added to c. So I defined it as a new c. So we have two parameters which we'll call it beta and alpha, where alpha is just the k, capital K divided by alpha. Okay, so all those numbers could be measured. These constants can be measured. Okay, if you're willing to take it all apart and measure the mass and figure out the shape and figure out the j and then figure out the damping coefficient, or we're gonna do something a little simple. We have a lab that does something simpler. Yeah. So what we used to do, is we looked at the transient response and identify the values of alpha and beta just looking at the graph, and that lab is taken out. Okay, so we'll actually give you what alpha and beta are. Okay, so just to tell you what that lab was about, we first consider the transient response to the step input voltage. V sub t equals, let's say it's just 3 volt, just made up. Okay, and I have an alpha and beta value which only I know. Okay, I'm not telling you what they are yet. So when I plotted the response, you have omega. That's gonna be constant. Okay, that's constant. Okay, you have this constant steady state value, and you have theta, which is growing linearly. Okay, that kind of makes sense because when you look at the first equation, what do you have? When the v is constant, you're going to have a constant solution, right? It's part of the total solution. Okay, so if you look at it a little more carefully, so you have, this is the equation. Okay, this is the equation right here. Okay, and then we apply the 3 volt. Okay, we apply 3 volt right here. I don't know what alpha and beta, and we have constant omega t, steady state value of omega t approximately equal to 8 radians per second. Okay, so we do know that omega steady state value is alpha Vn divided by beta. So what does it tell you? It tells you, since that's equal to 8, since this is equal to 8 and this is equal to 3, this tells you alpha over beta must be 8 over 3. Okay, that's not enough to find alpha and beta. Okay? I mean, this is actually a much better method than actually trying to figure out what the j, what's the damping coefficient, and what's the motor constant and all that stuff. So now what we're going to do is we're going to look at the transient response to find the beta. Okay, so how does it work? I need a little bit of space. So you have omega sub t has the following solution. We have a time constant. We have a characteristic root which is equal to negative beta. Okay, so you have some constant. Let's call it a. You have e to the minus beta t. Okay, plus your steady state solution, which is equal to alpha over beta times v in. Okay, and if you apply the initial condition where the initial speed is equal to 0, okay, and you'll find that a plus alpha over beta v in equals to 0, and we find a must be equal to minus alpha over beta v in. Okay, true. So you have omega sub t equals now alpha over beta v in, and you have the part that's exponential decay, but minus and plus 1. Okay, I took out the steady state response outside. So when you examine, okay, e to the minus beta t for the exponential function, okay, the time constant is defined such that it's the time at which it becomes, okay, e to the negative 1. Okay, at t is equal to some time constant, okay, e to the minus beta tau becomes e to the minus 1, okay, which has a value. It's about like 0.37, okay. So what is tau? Well, tau must be 1 over beta, okay. So let's go back to the tau, okay. When time is equal to 1 over beta, what does omega become? Omega becomes, oh, I meant to write, let's see, okay, I'll just write below. Here, omega at time constant equals alpha v in over beta. I'm just going from here to here, okay. Now you have a minus e to the minus 1 plus 1. What does that mean? Okay, what that means is that this is 0.37, okay, negative 0.37, so that means it's a 0.63, 63% of alpha v in over beta, where this is the value, this is your steady state value, okay, well the steady state value is 8, okay, 8. So when you multiply 8 times 0.63, can I just say 5? Okay, I don't have a calculator with me right now. So 5 did I just put the wrong unit? Radians per second. So when does it become 5? That time right there, let's call that 0.03, okay, 0.03. So right now I can read my time constant. Time constant is when the total response is 63% of the steady state value. That's about 0.03, okay, which is equal to 1 over beta, okay, 1 over beta. What is beta? And I think that's 33, okay. So I found beta right here. What is alpha? Alpha must be 88. Where did I get that from? I'll highlight the part. Can you figure that out? Okay, right here. Okay, right here I found from the steady state value, alpha over beta is equal to 8 over 3. Okay, so now, okay, should we answer this question? The time constant is the time it takes for the first order transient response, so it's e to the negative something t. Decay to what of the original value? Okay, this is talking about just the transient response only, okay, not the total response, just transient response. So what happened to the transient response? This system, okay, transient response is only this part right there, okay, that's your transient response. This one right there, that's your transient response, where this is your steady state response. So it decays to 37% of its original value. So anyway, this used to be our lab, and then we took this lab out. So you'll find that, oh, alpha was very close. Alpha was 80 and beta was 30. Okay, what did I get? I got 88 and 33, and let me see, that's more than 10% error. Okay, you will get marked wrong on the homework quiz, by the way. Okay, I think you have to be within plus minus 10%. Okay, so I suggest when you see this problem, you should really zoom in and use a straight edge. Okay, straight edge when you bring it down. Okay, use a straight edge and then try to estimate this value as accurate as you can. Okay, so I'll just print out the whole thing and then use a ruler and all kinds of stuff and magnify it maybe. So now our servo arm, it has a built-in potentiometer, okay, that will report the location of the arm as output voltage between -5 to 5 volt. Okay, what does that mean? Your location is no longer a degree or radians. Our location will be in terms of voltage. Okay, so should we do a little math? So if the voltage is 3 volt, if the voltage rate is 3 volt, what's the position of the arm then? What would you do? Okay, this will be, can we just do ratio? 3 volt to 5 volt. No. How do you guys do this? Let me see. Let me get rid of that. Okay, so So do you do 5 volt divided by 180 degrees equals 3 volt divided by x degrees? How's that? Okay. So that should give you 180 degrees times 3 over 5, which is 60%. I don't know, 100 and something maybe. Oh, I'm really multiplying. Maybe 108. I don't know. Okay, so maybe. Okay, so the answer is that one. Answer is right here. Okay, 180 times 3/5. So going back to my blue color. Okay, so you will provide the control law. Do you remember I said servo arm will be controlling the location, the orientation, and the position, the same thing, position of the servo arm. Actually, you will provide the control law that will do that. Okay, so for the actual lab, you have to be very careful so the arm does not hit anything. Okay, you want to give it plenty of space so that it doesn't hit anything, and then at no point you want to hold on to the arm, right, when it wants to rotate. So the control law, let's see, we have a plant. We have a plant, which is the plant transfer function is given by this. Where did it come from? It's given from d squared theta over dt squared plus beta d theta over dt equals alpha times v input voltage. Okay, the transfer function is given by your theta, it's a capital letter theta, s divided by v in s equals alpha divided by s squared plus beta s. So that's your plant transfer function. That means what's going in right here, it should be the voltage. Okay, and what's coming out should be the position. Okay, so this is when we have a plant only. Okay, so we put in the voltage we think we're putting in, but the thing is that D is there to include any disturbance in the system. Yeah, so disturbance must be in the unit of voltage so they can add them together. So this is your open loop. Okay, so when you have a plant only, so you put in the voltage you want, you get a theta, but the thing is there's no feedback loop, right? So we have no idea what the angle, what the position is. So the control law is first we're gonna do the open loop control with a compensator C. Yeah. So still, what's going into the plant must be the voltage. What's coming out of the plant is your angular position. Okay. And then before we decide on the voltage, what we're gonna do is we're gonna think about what kind of position, desired position that we want. Okay, and then we're gonna just make up some control law. Okay, and then the voltage calculated by the control law, and plus some disturbance that we don't know, and the plant is going to your arm is going to start rotating. Okay, and then it's going to output some position. Okay, so you realize there might be a little problem with that, right? Why? Because without any feedback, without really knowing what kind of position we have here, actual position we have here, there's no way of knowing, okay, whether we're getting the desired position, right? Yeah. So the better system will be put a feedback loop, meaning we have a sensor. Okay, so now we install a sensor and we monitor what the position is. Okay, what the position is, and compare it to the desired position. Okay, so what's coming out of here is the error. Okay, if the error is positive, that means your desired position is greater than the actual current position. Okay, and then you use some kind of control law and calculate the voltage that you want. Okay, but the voltage that actually goes into the plant may not be same as what you calculated. Why? Because of the disturbance D. Okay, but this is a big improvement. Why? Because now we monitor the current position. Okay, and then the error is the actuating signal. Okay, so if the error is equal to 0, okay, you'll and then this line becomes a 0, right? Okay, 0 times c will be 0. Okay, and hopefully maybe the plant will get 0 volt and nothing will happen, but that's not going to happen if you have a disturbance. So the next slide. So let's try some open loop control. Okay, open loop control. So people have actually thought about this before. Okay, so people thought, so this is open loop, so there's no sensor. Okay, we have no idea what the position is, current position is, but we do know what kind of position that we want it to have. So it's like saying, oh, you know what, I want my arm to go to 30 degrees, but there's no way of knowing it. If you're really into 30 degrees, I have no protractor, I have no way of knowing. Okay, so let's make the disturbance to be 0 for now. Okay, so people actually thought about this, and they said, you know what, why don't we make the compensator to be exactly 1 over the plant? We know the plant, don't we? Right? Maybe. Okay, so why don't we call this one, why don't you make the c to be 1 over p? Okay, in that case, shouldn't the theta d be same as theta? So what does that mean in time domain? Yeah, what does that mean in time domain? So this technique is called the inversion. In time domain, what we're doing is we calculate the voltage needed to achieve the desired angle and use it as an input to calculate the output angle. Did you get that? Okay, did you get that? So this is an actual example. So this is the equation. Okay, so alpha is 30, beta is 80. So this is actually, if you remember the actual equation, theta double dot plus 80 theta dot equals 30 times your V in. Okay, so what we're going to do is, you know what, I want my theta d to be 1 radian. Okay, but there's no way my theta d can become 1 radian over, immediately. Okay, so what we're going to do is we're going to put in 1 minus e to the minus 4t, where my desired theta d has a smooth curve from 0 to 1, like that. Okay, so this is your time, this is your theta desired. Okay, it will go to 1 radian, in short time. Okay, but there's no jump from 0 to that. So substitute this into the EOM. Okay, put this into EOM. Okay, then you calculate them. Since we know theta d, why don't we calculate? We can calculate what's the voltage required to make that happen. Okay, so now we go back to the original differential equations, right? And then put in the VT. Okay, the V that we just calculated in there. So what do you think is going to happen? I mean, in MATLAB world, what's going to happen in MATLAB world? Perfect. It's going to be perfect, actually. This was a theta desired, and then that's what we will get. Okay, so I mean, it looks perfect. So what's the problem with this? Many problems. Okay, you'll have a big trouble if the initial conditions do not match exactly. Okay, right? I mean, I calculated my V in assuming all my initial conditions are 0, right? But in real life, what if the initial conditions are not zeros? Yeah? And another one, you'll have a big trouble, you'll run into big trouble when the small disturbance is put in. So remember, disturbance is something we don't know, okay? A lot of times we don't measure it, we don't know what it is. Yeah? So if there's a little disturbance, then this is not going to work, okay? Imagine in this, okay, if the D is not equal to 0. Okay, so you have voltage that's not, you might calculate the voltage exactly here, but if you add, okay, a small disturbance, you're not going to get the exact theta desired as an output. Okay, another one that's not mentioned here is that how sure are you about the plant? Okay, another one, so we do not know the plant P sub S exactly. Okay, we modeled as a second order system. Then what did we do? Then we say that inductor is small, inductance is small. We arbitrarily got rid of it, and then we estimated alpha and beta. Okay, so we don't know the plant exactly. We don't even know the order of the plant. Okay, so this method will not work. Okay? But it's a neat idea though. So let's talk about the closed loop PID control. So when you have a closed loop, okay, so your C compensator will have, so this is a PID control. So you have a proportional part, this is integral part, and this is derivative part. So you have a PID controller where what do? we multiply the error signal by Kp, and we multiply the integral of the error signal by the Ki, and then we multiply the derivative of the error signal by Kd. Okay? And then goal of how do we choose Kp, Ki, and Kd? Basically, we have two goals. Okay? We want good transient response, and we want to have no or small, very small steady state error. Okay? We want to have a good transient response, and we want to have a good steady state response. And for the transient response, the bare minimum is that we have to have a stable response. We can't have a theta going to infinity. When we say, oh, go to 30 degrees, we don't want it to be just going to infinity, or just keep spinning. And we will also like to have a reasonably fast transient response. When I tell my arm to go to 30 degrees, I want that to happen I don't know, 1 second, under 1 second. Okay. I don't want to wait until tomorrow, okay? Tomorrow until it goes to 30 degrees. So we want to have a fast enough transient response. So now, so let's deal with, let's find what controls a transient response. The transient response is being controlled by the what? Characteristic roots, right? Characteristic roots. So how do you find the characteristic root? Find a transfer function of the system. Okay, so I found the transfer function theta over theta d and theta over disturbance, because we have two inputs, you have two transfer functions, any. Okay, and then you realize we have a characteristic equation equals to 1 plus compensator plus the plant equals 0. Okay. And then we'll be finding the root of the equation soon. Okay, so now let's look at this is for the transient response. Okay, this controls the transient response. Okay, to study the steady state error, you have to look at the error E right there. Okay, with the transfer function E over theta d and then E over d, you have to have these transfer functions ready. So looking at the steady state error first. I looked at the E over theta d and the E over d. Why? Because it can be done in one slide. So this is a little shorter than the transient response. So when I actually substitute in the C of S and then P sub S, do you remember what C and P were? P was alpha divided by S squared plus beta S, and C was, you have a Kp, Ki, and Kd. Okay, so when you plug these two in, you find that E over theta d equals this, and right away you can tell this is a type 2 system. Okay, just looking at a square, you have a type 2 system. What does that mean? You can put in a parabolic input. Okay, input that varies with t squared, and it will still be able to track it. Okay, if I put in a angular position to be t squared, it will still be able to follow it. Okay. How about disturbance input? This is type 1 system. Okay, type 1 system. What does that mean? Even if you have a disturbance that's varying linearly, okay, with time, our system will be able to track it, track the motion, track what we want. Okay, with no error or with a steady state error. So when we have a step input, which is a 0th order input, okay, so having a type 2 system with respect to the desired input, okay, and the disturbance input, we're not going to have any steady state error. So this just tells you for the step input, okay, that means they'll have no steady state error. Okay, so that's good. Okay. So what if the Ki becomes 0? What if this term disappears? What if we're using instead of using PID control, what if we use PD control, and then we reduce what? You reduce the type number, right? This will become type 1 because S and S will cancel. This will become type 0. Okay, even in that case, we should be able to handle the step input. Okay, we might have some steady state error, but we should be able to handle it. So now, looking at the change in response, we have to look at the denominator of any transfer function. We find that the characteristic equation is a third order. So what is this one? This is 1 plus c times p equals 0 with this will have some denominators, so we'll multiply by the common denominator and then make it into polynomial. So what are the roots of this polynomial? You should have 3 roots. Okay. The thing is, this is difficult because this is a cubic, this is a third order, and nobody remembers, okay, the cubic formula. Okay, we can use computer to solve a cubic equation, but when the coefficients are unknown, we can't do that. Okay, so now what we do is to make one assumption, which is if you have a small k, you should really check this. Okay, if you have a small k, we can rewrite this as this times s plus ki over kp. Okay, and you're gonna compare this with the standard second order characteristic equation, and you find that beta squared plus alpha times kd is 2 times the damping ratio times omega n, and then alpha times kp is omega n squared, written right here. Okay, written right here. Turn that I don't actually have to rewrite it. So and that means you're gonna have roots. Okay, that means you're gonna have roots. Let me write it right there. Okay, you're gonna have roots where s equals to minus zeta omega n plus minus omega d I. Okay, where omega d equals omega n times 1 minus zeta squared. Okay, and we have another root which is a negative ki over kp. Okay. Yeah. So let's think about the step response specification. When we have a second order system, first of all, we don't have a second order system, right? We have a third order system where the two of them we're assuming to be second order roots, meaning complex roots, and we have a third root which was negative ki over kp. Okay, so from the second order underdamped system, this is this number right there. Okay, this is called the steady state response. Okay, and this distance, okay, this distance divided by x, that distance divided by xss, it's called the percent overshoot. I guess to make it a percent, you might have to make it multiply by 100. Okay, and rise time 10 to, this is the 10 to 90% rise time is how long it takes for the response to go from 10% of the steady state value to 90% of the steady state value. Okay, for the first time. So this is called the rise time right there. Okay, and settling time. So sometimes we use 2%, sometimes we use 1%. So if you recall, 2% definition goes like this. 2% definition is about 4 divided by zeta times omega n. Okay, so whether it's 1%, 2%, 3%, the only thing will change is the numerator, the number for the numerator. So anyway, 1% settling time is how long it takes for the response to die down settle between plus minus 1% of the steady state value. Okay, so this line right there must be 99% of the x steady state, and what do you think? This line must be 1.01 times x steady state. Okay, so this is a time when the response goes inside that band and never come back out again. Okay. So let me see, and this capital N, this is the number of oscillations before the settling time. So this is number of oscillations, and this is approximately, okay, about 3/2 times square root of 1 minus zeta squared divided by pi zeta. Okay. So this is what we learned either in ME 3333 or the controls. So when we give a step input, okay, when we give a step input, that's what the response will look like. Okay. So I wanted to point out about the rise time. So rise time has multiple formulas, and we're gonna use which formula? We're gonna use 2.16 times zeta plus 0.6 divided by omega n, and another alternate formula is 1.8 divided by omega n. Okay, and this is rise time that I actually calculated numerically for many different cases. So this is the actual rise time. Okay, that's a function of zeta. Okay, and then this line right there, I'm just gonna make it to red. Okay, this line right there, this is a 2.1, what was it? 2.16. Yeah, zeta plus 0.6 divided by omega n. Is that right? Yeah. Okay, that's that line right there. Okay, so assuming using this, okay, using this expression is not so bad. Okay, but that there was another expression for the rise time. Which one was? What was that? 1.8. Okay, 1.8 divided by omega n. Okay, they'll put the graph right here. Okay, this is 1.8 divided by omega n. Okay, and you can see this is not a good approximation. Yeah, so I can't remember which control book uses that, but anyway, we'll be using 2.16 zeta plus 0.6 divided by omega n to be the rise time, 10 to 90% rise time. So this is what we're going to do. So we first, given the system parameters alpha, beta, and desired omega n and zeta, what we're gonna do, we're gonna choose Kp and Kd such that Kp is chosen by this equation. Where did that come from? And omega d is chosen by this expression. This came from, okay, this came from right here. Okay, where the omega n squared is equal to Kp over Kp times alpha. So if you know the omega n that we want, how do we choose Kp? Kp is omega n squared divided by alpha. Okay, once you choose Kp, you move on to Kd. What is Kd? 2 zeta omega n minus beta divided by alpha. So that's what this equation is saying. So now, given desired time constant for removing steady state error, we're going to choose Ki equal to Kp divided by tau. How did that work? We have, remember, we have 3 roots. Okay, 3 roots. So you'll see when the Kp is small, this will become a dominant root. And this will ultimately control how fast, okay, how fast your response can reach the steady state. Okay, and you have a root which is equal to, I'm calling the root s, minus Ki over Kp. Okay, what's the time constant? Time constant is Kp over Ki. Okay, so how do I choose Ki? Ki equals Kp divided by the time constant that I want. Okay, so that's what it's saying right here. Okay, your dominant root is equal to minus Ki over Kp. So you have an expression, you have exponential function e to the minus Ki over Kp times t multiple in the response. Okay, which will dominate, which will be the slowest to decay. So that will control them, how fast you can remove the steady state error. So now, example. Okay, what are the desired values of omega and zeta? Where do you get that from? Well, you get that from the step response specification. Okay, so from here, your customer will tell you, oh, I want the settling time of 10 seconds. I want the overshoot to be 20%, under 20%. Okay, do something like that. Okay, so in this case, I said, oh, let's say the customer wants 5 oscillations before the transient response dies out. I guess that's a maximum oscillation. And the rise time of 0.1 second. Okay, so in that case, you use these 2 equations. So the first condition will give you what? Zeta. Okay, this will be 5 equals 3 halves square root of 1 minus zeta squared divided by pi times zeta. Okay, that's 5. And find what zeta is. Okay, once you know zeta, plug it in here. In the rise time, we want it to be 0.1 second, and you find out what omega n is. Okay, so you should obtain these 2 values. So you should really pause the video and then see if you can get those numbers. So now, do you think it's going to work out? What if you use, so if you use these two numbers, do you think we're going to get 5 oscillations before it settles down and the rise time of 0.1 second? So I did some MATLAB experiment. Okay, I did a step response of, so I used a transfer function which was 1 over 1 plus 2 zeta omega n, what happened to my s? S square, s plus omega n square, and I stuck in omega n square so that my steady state response will be 1. Okay, so I found the step response right here, the first line. Look, 1, 2, 3, 4, 5 peaks before it settled down, maybe 5 or 6. Okay, doesn't matter, it's approximate formula anyway. Okay, so that's pretty good. And how about the rise time? So that's really hard to tell, because 10% to 90%, what's from here to here, that's your rise time. I can't read, so I use this, what's called step info. Okay, step info, and it says rise time is 0.14 second. What was the desired rise time? 0.1 second, right? That's not so bad. Okay, so you'll find that in controls, you have to deal with, you have to learn to accept numbers that's not quite what you wanted. Okay, so let me see. So I wanted to check again. What's the settling time? They use as I remember, I think they use a 2% settling time, I think. So settling time is 5 seconds. 5 seconds around here. Okay, so sure, how many peaks before it settles down? About 6. Okay, 5 or 6. To me, they're the same numbers. So now, summary. For the second order underdamped system, we have the following equation that will what? That will connect them what the customers want, such as it will be given in terms of not zeta and omega, and it will be given in terms of settling time, rise time, or the percent overshoot. Okay, then you have to figure out. Okay, so given let's say TS, TR, MP, what else? What was it? Number of oscillations. Then you have to calculate desired omega n and zeta. Okay, and given omega n and zeta, you have to figure out what kind of KP, KI, and KD, okay, you use for the controller. Okay, and then these are the equations that you need. Okay, you need to calculate those. So given the values, and you can calculate the omega n and zeta. So that's a green box. Given the omega n and zeta, using these equations, you have to find the Kp and Kd. Okay, and then actually we had one more time constant. Okay, so and then this is in the lab. You'll be asked to fill out the following table, and I filled out some of it. So what's the effect of having increasing zeta on the rise time, overshoot, and settling time? Okay, I feel that much, right? So that's this one. It's like not applicable. Okay, so there's nothing in it. So what about increasing omega n? Okay, and then okay, what is the effect of Kp, increasing Kp, Kd, and Ki on the zeta and omega n? Okay. So in the end, you have to fill out a table like this, okay? Where when you increase Kp, Kd, and Ki, what kind of effect do they have on the rise time, overshoot, and settling time? So this table is not filled out right now, okay? So it will be your job to figure out as best as you can through experiment or equations, how these 3 parameters will affect those 3-step response specification parameters. Okay? And this is the end of the lecture. Okay, thank you, and I hope you had a good semester despite not having to come to school. And I wish you best of luck and good luck with your job hunting. Okay, thank you. Bye bye.